What I'd like to do in this segment is talk about how we actually carry out integration of the different terms that show up in our weak forms. And I'm referring specifically to the fact that when we carried out the formulation for linear and quadratic basis functions, we explicitly carried out certain integrals, which we could do, by the way, because we assumed that our coefficients of the problem, our coefficient E, if we were talking about elasticity, or it would be something like a conductivity if we were talking about some other problem, that coefficient was uniform over the domain. We also did the same thing for the forcing function, right? The distributed forcing function, F, we said was uniform over the domain. It made our integrations fairly easy, okay? However, that's not always the case. So, we will need to develop the ability to carry out numerical integration. Okay? It's needed if the coefficients in our problem, such as E, our forcing function F, and other quantities, maybe the area A and so on, are complex, or let me say complicated functions, right? We're not really talking about getting into the complex space here, but we need them, however, if E and F and so on are complicated functions, right? Functions of position X. Okay? All right. We could also need them if the sort of basis functions we need are very high order, right? Then sometimes integrating them, or if all of those basis functions are something more complicated than the simple sort of polynomials we're using here. Okay? All right. Also, if complicated basis functions are used. Okay? Now, so we are going to develop numerical integration for this. In particular, the approach that we will take is what is called Gaussian quadrature. Okay, we will consider Gaussian quadrature, which can be shown to be optimal for polynomials. Okay, by optimal we mean that it's possible to integrate certain types of polynomials of certain order exactly. Okay. Right, and there's a systematic rule about how we go about doing this. All right, so let's see what we need. If you look back to any of our integrals, either the integrals going into the stiffness matrix or into the distributed forcing function, you will see that we always are faced with the task of integrating over -1 and 1 a function of the form g of c dxc. Okay? The whole business with any sort of numerical integration, any sort of quadrature, is the following. We replace it with a sum, okay, over L, going from 1 to n int, where n int simply means number of integration points. Okay? We replace it with a sum where every term in that sum, in that series, if you like, is in that finite series is G evaluated at a certain value of C indexed by L, multiplied by what we will call a weight for L. Okay? This is the general form of a quadrature rule. Alternately, a numerical integration rule. Let me say a few things here. N sub int is the number of integration points. Okay. CL is an integration point. Okay, WL is the corresponding weight. Weight ascribed to the integration point. Okay, here of course L goes 1 to n int, and here too. Okay, now essentially the way to understand this perhaps is to say that, well, if this is what we're trying to do, if this is C and this is our function G, and maybe G looks like that, and we are here between -1 and 1, right? What we're trying to do here is pick certain points, say that is CL, one of those CLs. We look at the value of G, right, at that value of C, right? So this is G at C sub L, okay? And we are basically forming that sum like I wrote on the previous slide. Okay, we're giving some certain weight to the value of G x CL. All right, okay, and then there are just rules, right? Before we get to those rules, let's just say one more thing. The weights WL are such that sum over L going from 1 to n int WL has to be equal to 2. Can you think of why this might be the case? Why do we have this requirement? It's because if G of C is a constant, we know that integral -1 to 1 gc dc is equal to twice of that constant, right? Right? Well, this is satisfied automatically by saying that when we sum over L, G of CL, WL, if that is a constant, and this rule for WL is satisfied, right? For the WLs is satisfied, we get back twice of the constant. Okay, so we ensure that at the very least we can integrate constants exactly, right? So Okay. All right. Here are the integration rules. Okay. So n int equals 1. Okay. For this rule, c1 equals 0, right? And w1 equals 2. For n int equals 2, we have c1 equals minus 1 over root 3, w1 equals 1, c2 equals 1 divided by root 3, w2 equals 1. Going on, n int equals 3 has c1 equals minus 3 over 5 square root, w1 equals 5 over 9, c2 equals 0, w2 equals 8 over 9, c3 equals 3 over 5 square root, w3 equals 5 over 9. You can check that for all three rules I've put down, the sum of the w's is always equal to 2. Okay, these are all rules from Gaussian quadrature. Right, and it goes on, right? We can write out rules for any order of n int. Okay? I mentioned that Gaussian quadrature is optimal. It is optimal in the sense that a Gaussian quadrature rule with n int points, right, n int integration points, exactly integrates polynomials of order lesser than or equal to twice n int minus 1. Okay, so if we go back and look at n int equals 1, it integrates linears exactly. N int equals 2 integrates up to cubics exactly. N int equals 3 integrates up to pentics, right, and so on. All right, that's what we need to say for numerical integration, and we'll end this segment here.